So now we're gonna do the same parameterization, but in this case it's a parameterization of two auxiliary variables. So again, we use the relation that we have f of x, y, y prime equals to f of x, y, p equals to 0, with p defined to be y prime, right? I always say that this curve, this function, or this relation here describes a 2D. It describes a 2D surface in 3D, in this, right, r cubed, with the coordinates being governed by x, y, and p. So in the space x, y, and p, right, this thing defines a 2D surface. So in this case, let's say we can parameterize this using two auxiliary variables. So that means that we basically, this is equivalent to stating that x is equal to, in this case, this function of u and v, and y is equals to eta as a function of u and v, and p is equals to this as a function of u and v, right? And in this case, this is zeta and this one is xi. So I always confuse between them because they look pretty similar. So this is zeta and this is xi and this is zeta, right? Okay. So now we're gonna find dy, we're gonna find dx, and we're gonna find p, right? Because we have the relation that dy over dx equals to p equals to y prime, so dy is equals to p dx, right? So now we're gonna find dy, dx, and p. So in this case, dy, since it is governed by a function of two variables, we're gonna use a differential definition for a two variable function. It will be dn over du plus du plus dn or eta over dv, and then dx is similar, but in this case it is xi, so d of xi over du plus d of xi over dv. In this case, we don't need to find the differential of p because p is just given, right? So now we find the relation. We write that dy, we substitute for it, d eta over du plus d eta over dv equals to p, which is just wait, hold on, what is that called again? That one is called zeta, right? So that we said p is equals to zeta, so it's zeta. How do I write that? It's like this, right? Zeta multiplied by dx, with the dx being defined like just d of xi over du plus d of xi over dv, right? So what happens now is that we can just create essentially a symmetric form now. So it's d eta over du minus d minus whatever this is, I forgot its name again. This d xi over du all multiplied by du plus in this case this one will be d of eta over dv plus d minus d this thing which I forgot its name multiplied by d xi over dv. So we obtain this equals to 0, and this is essentially an exact, or is a symmetric first order differential equation, and suppose that we have found its solution, which is v equals to v of u and c, right? So now we can describe x to be just, we can describe a curve, a parametric curve, that is a solution to this fxyp. So in this case we have v is equals to uc, x was equals to xi of u and v, which is equals to now xi of u, v of u and c, and similarly y is equals to eta of u v equals to eta of u v u c. And that is basically what you do. You obtain a parametric solution. So this is the method for obtaining a parametric solution for a general form of a first order differential equation. And yeah, that's pretty much it. There's not really that much assumptions going on over here. The only assumption here is that you can basically define parametric. You can define this curve or this surface as a parametric surface. So this is the assumption. We can take the function over here that is defining the first order differential equation in the R space x, y, and p, and parameterize it in terms of u and v. Then you can obtain a parametric curve. You can obtain a parametric curve that suffices or that solves the first order differential equation, and that's it.